class we are doing one thing in a hurry. So, maybe I just start from that and do it again. That is, suppose there is a random continuous valued, that is analog random process x a t, okay, and this is sampled at a time period, sampling period of capital T to generate a sequence x n. So, obviously, x n also is a random sequence. So, you have x n equal to the nth sample. That is, if you sample at t equal to 0, then small t equal to capital T, then twice t, 3 t, so on and so forth. The nth sample, I call it x n, the nth sample of the sequence x n, that is equal to x a n t. So, obviously, x n also is a random sequence. X a t has got this autocorrelation, sorry, this is the autocorrelation R a tau. If you take the Fourier transform of it, you get the analog power spectral density, that you denote as phi a for analog, j capital omega is radian per second, which is the analog frequency. And x n, this has got the discrete correlation function, or maybe you can say R k or R n, say R n or R k, does not matter, there must be an integer. This has got the discrete time. If you take the discrete time Fourier transform, then you have got the corresponding discrete time power spectral density phi e to the power j small omega. Small omega is just an angle, radian. Okay. Question is x n is x a n t. So, that is the time domain relation between the two processes. So, what is the relation between the two frequency domain functions? One is the analog and is the discrete time version of the power spectral density. Analog power spectral density vice versa discrete time power spectral density. So, we just derived the result yesterday, and I thought I think that I did it in a hurry because I was running short of time. So, maybe it won't be bad if I just spend some more time on it, not much time, but just little more time and do it once again. So, that that important thing is kind of well understood. So, what I do, we know that x n is equal to the inverse Fourier transform relation small omega is a variable of integration. So, you can put it omega, omega prime, theta, alpha, beta, anything, but n is your choice coming from outside x of n, that is you want to find out the sequence at n. So, that n is put in here inside the integral. This relation we know, but at the same time we know that x n is nothing but x a n t, and x a t is the inverse analog Fourier transform of phi a j omega evaluated at time t. So, there instead of time t, if we write n into capital T, then we will get back x a n t. So, that is analog inverse analog Fourier transform phi a j omega e to the power j omega, not small t, but for a specific value of small t, that is n into t. That is I am evaluating the integral at a time n into capital T. That will give me the value of the function at a point, value of the function x a t at a time n into capital T, and that is nothing but equivalent to x n. Then my purpose will be to manipulate things, so that this integral from minus infinity to infinity, it is I mean made to, it looks identical to, or it is made to look identical to the previous integral from minus pi to pi. There is the two integrals I want to convert into the same form. Therefore, by comparing terms I can find out a relation. Okay, that is my goal. So, here what I do, this is an infinite integral. So, integral is from over the real axis capital omega from minus infinity to infinity. So, this whole integral I write as an infinite sum of some finite integrals. Okay, I will be dividing the entire real line into small non overlapping segments. I will carry out the integral over all those segments, okay, and my segments will start from minus infinity and go at plus infinity. If I do that, it will be like this. It will be like this. This is my omega axis, this is my origin, So, I will have one slot or one sector from minus pi by t to pi by t, this I call it 0th, then pi by t to 3 pi by t dot 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 rth will be where? You see, for 0th my the sector is from minus pi by t to pi by t, center is 0. Then the first is here, the center is at 2 pi by t, and we go pi by from 2 pi by t, we go pi by t to the right and pi by t to the left to go to meet the two boundaries. So, for the rth case also, the center point will be 2 pi r by t, and from there I go to the right by pi by t and to the left by pi by t. So, I meet the two boundaries. So, what I am doing, this entire integral I will write as a summation of integral over this 0th sector, then first sector, second sector, dot 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 rth sector, and this I will go on starting from the minus infinity side to the plus infinity side. If I do that, that means this integral I am writing as a summation over r, rth, I write the integral for the rth slot or rth sector, and then r will be from 0, 1, 2, 3 dot dot dot, and on the other hand minus 1, minus 2, minus 3 like that. So, the rth case will be what? 2 pi r by r t, 2 pi r by t minus pi by t. So, 2 pi, maybe I write as 2 r minus 1 pi by t, 2 r plus 1 pi by t, and rest is same. Okay. Then I have got a double summation, one is the discrete summation over r, another is this integral, and assuming that both exist, they can be interchanged. Unfortunately, we cannot interchange here, because I mean if I interchange the outer summation is integral, but its limits contain r, whereas the inner summation is over r. So, once the summation is done, r disappears, but at the same time r exists in the limits of this integral. So, that means I have to do something so that the r is made to disappear from the limits of the integral, then I can do the interchange of the two summations. For that matter, what I do, I now introduce a new variable, I just shift the origin in this figure, from here I shift the origin to here. There is I introduce a variable omega prime, and later I will call it as omega again, but for the time being it is omega prime as omega minus 2 pi r by t. If I do that, then you see d omega and d omega prime are same firstly. Okay. Omega is omega prime plus 2 pi r by t, d omega prime are same. There are two limits of the integral. When omega is 2 r plus 1 into pi by t, omega prime takes the value pi by t, and when omega is 2 r minus 1 into pi by t, omega prime takes the value minus pi by t. Okay. So, that means here only I do some change, because I do not have space to take one more step. Minus pi by t. So, you see r has disappeared from the integral limits, and what I have here phi a, not j omega, because it is now in terms of omega prime. So, j omega prime plus j 2 pi r by t into, the interesting thing is e to the power, you see omega is to be replaced by omega prime plus 2 pi r by t. One term will give rise to e to the power j omega prime n t, the other term e to the power j 2 pi r by t, and then outside n into t. So, t and t cancels and you get e to the power j 2 pi r into n, r and n both are integer, and remember e to the power j 2 pi into any integer is always 1. So, that is why I do not write that factor here, and d omega prime are same. So, I can write as d omega prime, and then you can ask, I can take your permission to convert omega prime into omega again, because after all it is a local variable of integration. We are more used to handling the variable omega rather than omega prime. So, why carry the notation omega prime? Again bring back the same notation omega, though it is not the same omega as used earlier, it is actually the omega prime, vice versa is the previous omega, but I am now forgetting entire thing, I am just calling it omega without any relation to the previous omega. Okay. And the two summations now can be interchanged. Okay. So, that means this outer summation can be brought in inside, sorry, okay. One more thing I do now, this capital omega t this capital omega t, I introduce a variable small omega as capital omega t. Capital omega, its unit is radian per second, unit of time t is second. So, omega into t is just an angled radian. So, that means if I make the substitution in the integral, then first you see when capital omega becomes pi by t, omega becomes pi, and when capital omega becomes minus pi by t, small omega becomes minus pi. So, limits of the integral now are from minus pi to pi. Okay. So, what do you have in the integral? This integral now becomes equal to 1 by 2 pi minus pi to pi summation okay. Rest I will write later. What is d capital omega? D capital omega is 1 by t d small omega. So, that means I will have 1 by t here, and to the extreme right I will have d small omega. Then phi a j, you can write capital omega, you can substitute by small omega by t. I still my style is to still write it as capital omega. Okay, I will tell you what I do. I do not write it in terms of small omega here, and then this remains same as before, 2 pi r by t into now e to the power j capital omega n t. Now, capital omega t is omega, small omega. So, it is just e to the power j omega n. And after doing this, I mention separately that what is this capital omega? This capital omega is such that capital omega t is small omega, where small omega is used in the integral. So, actually either you can replace capital omega by small omega by t directly here, or you can still retain the notation capital omega, but give the meaning of capital omega separately, that capital omega is nothing but small omega by t. I prefer this style. Now, if you compare the two integrals, you see left hand side in both cases are x n, and right hand side also the two integrals are exactly alike. You have got d omega in both, you have e to the power j omega n in both, minus pi to pi, both the integrals are 1 by 2 pi and all that. So, by comparing you can easily see that x e to the power j omega is this quantity and this quantity, they are same. You can compare, these two are same. Okay. So, sorry, this is not x, I made one mistake. And this is not x, this is actually r. And this is phi. Okay. Because we are dealing with autocorrelation, not the actual sequence, but it is autocorrelation function, analog and discrete time. Okay. So, these two functions are same. So, this gives us a relation between the analog and discrete time PhDs, power spectral densities. We just take its meaning what it is. So, I write down the relation separately again. And then you substitute this as this. What it means that suppose phi a omega has been like this. Okay. This highest frequency, this is actually typical figure of band limited PSD. So, this is a band upper this after omega h, h for high, this perspective turns out to be 0 and minus omega h. Now, suppose, but what I am saying now has got nothing to do with band limited nature. I just took a figure like this. Suppose this is given to you phi a omega or phi a j omega, if you call, does not matter, because it is j is nowhere present, it is a real function. Okay. Okay. That means, if you choose a digital frequency small omega equal to capital omega into t, and you want to find out the discrete time power spectral density phi e to the power j omega at that digital frequency small omega, how will you compute? Okay, you have to carry out the right hand sum. So, what you have to do is this: first you plot as a function right hand side as a function of capital omega, then only I will transfer capital omega, change capital omega to small omega. So, right hand side summation, I do not count for the 1 by t factor, because it is just a scale factor. Right hand node summation, say for r equal to 0, you have got this only phi a j omega. Okay. Then r equal to 1, say r equal to minus 1, phi a j within bracket omega minus 2 pi by t. So, the entire thing will be shifted to the right by 2 pi by t. So, if your 2 pi by t is here, then you will have another function here, and for r equal to plus 1, j omega plus 2 pi by t. So, if 2 pi by t is here, minus 2 pi by t, this entire thing will be shifted here. Then at 4 pi by t, at minus 4 pi by t. And now we have to superimpose. You understand that if the overlap exists between all these shifted versions, then obviously the resulting function on after the total superimposition will no longer resemble the original phi a j omega. So, there will be distortion, we call it aliasing. For aliasing distortion not to take place, this 2 pi by t should be where? If 2 pi by t is, and what is 2 pi by t by the way? 1 by t is a sampling frequency, 2 pi by t is analog sampling frequency in radian per second, t is the sampling period. So, 1 by t is the sampling frequency in hertz, 2 pi by t is sampling frequency in radian per second, we call it omega s. So, if omega s, suppose omega s is greater than equal to twice the band limiting frequency omega h, then what will happen? Suppose this is your omega h, I am not drawing in the same scale because I do not have much space to my left here. So, I am making it narrower. So, suppose this is the thing, and omega h 2 pi by t, that is omega s is here. So, when this entire thing is shifted, there is no overlap. Similarly, minus 2 pi by t is here, here. So, there is no overlap, there is no aliasing distortion. And now, if you convert it into small omega axis, you always see one thing, how will you convert? Small omega is capital omega into t. So, therefore, what was earlier capital omega h, that will become small omega h is equal to capital omega h into t. Similarly, on this side shape will remain same. Remember one thing, capital omega s, that is 2 pi by t, whatever be the t, 2 pi by t, that radian per second, that is analog sampling frequency, what omega does it give rise to? If you multiply it by capital T here, t and t cancels, it will always give rise to 2 pi, no longer t is no longer present. So, analog sampling frequency is always, always gives rise to small omega equal to 2 pi. So, this will map to 2 pi, and half sampling frequency which is here, it will be at pi. So, something like this. Okay. Now, my claim is that suppose this is indeed given, that the analog power spectral density is given to be band limited up to some frequency capital omega h, and we follow this Nyquist rate of sampling, that is sampling frequency capital omega s is greater than equal to twice of the band limiting frequency omega h. In that case, if you take the discrete power spectral density phi to the power j omega, there will be no aliasing. So, whatever you see from minus pi to pi, that is between in the range of half sampling frequency on either side, that is an exact replica of the original analog power spectral density. Okay. Only thing is, from here, from this discrete time power spectral density, if you have to go back to the analog one, only thing you have to do is from small omega you have to go to capital omega by this transformation small omega equal to capital omega into capital T, and there is of course a 1 by capital T factor, there is a scale factor that you have to absorb. Okay. You get back the original power spectral density. If that be so, then for to measure the power spectral density of any analog random process, real life analog random process, what you have to do is this: we must sample it maintaining the Nyquist rate, and once I have got that discrete sequence, I develop algorithm which will work on the discrete sequence, because algorithms mean I will be using a computer that can work only on discrete data, not on continuous data. So, my algorithm will work on the discrete data, okay, and it will be a good algorithm. So, the power spectral density, discrete time power spectral density will be estimated to a good amount of accuracy, and once that is known, from that I will obtain the analog power spectral density just by transforming from small omega, going from small omega to capital omega. So, henceforth our all efforts to estimate the power spectral density will be concentrated on the digital side, that is estimating the discrete time power spectral density by developing some algorithms which work on discrete data. Assuming that band limited analog power spectral density was band limited and Nyquist rate of sampling was Nyquist condition of sampling was maintained, I have nothing to lose. From the discrete time power spectral density, I can get back the analog power spectral density just by the transformation small omega equal to capital omega t. Okay. I can just quickly take an example. Suppose for an analog signal is given like this: 1, some t, this is not sampling period, this is just a t, and minus t. Okay. Question is, what it is phi a j omega or phi a omega. You can see one thing, how do you get this function? If you have a rectangular function from t by 2 minus t by 2 and area is 1 by t, height is 1 by t, the area is 1. If you convolve this function, you can call this function x t. If you convolve this with itself, that is, if you do what you get, you first reverse it and you have to go on shifting it. If you reverse it and do not shift, that is the two functions come one below the other, then you have maximum overlap. Okay, you just multiply the two functions and calculate the overlapping area, where overlapping area in this case will be 1. So, that will be the value at 0 shift, that is at t equal to 0. Then you shift it to the right, say by t. That means this much area, if you shift it by tau, then how much area goes out? Tau into 1 by t. So, net area is previous area, that is equal to 1 minus tau by t. So, as tau increases, tau by t also increases. Okay. So, the correlation decreases. So, it is like actually it falls down linearly like this, 1 minus tau by t at tau equal to t, this touches 0. After that, there is no overlap, one rectangle has gone purely out of the domain of the other integral. So, there will be no overlap and value will be 0. Similarly, on this side also, if you shift it to the left, it will fall in a linear manner like this. The function here will be tau by t, because tau takes negative values, and you get back what it is. So, you can see R A tau is a convolution between one rectangle and itself. A rectangle is what? Height 1 by t and duration from minus t by 2 to t by 2. So, that means what will be the analog Fourier transform of R A tau? This will be nothing but square of the Fourier transform of the rectangle function. That is, we know sinc function, it will be sinc square, okay, because you know convolution in time domain is equal to product in the frequency domain. Okay. So, just the x t is convolved with itself, that means the power spectrum, this Fourier transform of x t has to be multiplied by itself, okay, and you will get back this. So, what is the, for a rectangle, what is this? If you take the rectangle, what is the Fourier transform? That is sinc, but what is the exact expression? It is very simple to do. That is height is 1 by t e to the power minus j omega tau, j capital omega, sorry, d tau, and that is equal to 2 j, and j will cancel because j tau will come below. You can quickly tell me what it will be. 2 j sin t, and this is equal to actually sin omega t by 2 divided by omega t by 2. So, this phi h omega will be square of this function, sin omega t by 2 divided by omega t by 2 square. Sorry, this is capital omega, I am making a mistake every time. If you plot it, it is a sinc square, so it will be always positive, it will be like this. For the zero crossing frequencies, whenever numerator becomes 0, that is omega t by 2 is equal to say pi or 2 pi or 3 pi like this. So, 2 pi by t minus 2 pi by t, 3 pi by t, so on and so forth. Okay. And then is it band limited? Theoretically no, but practically yes, because you see this function is phi h omega rapidly falls down to 0. So, maybe when you are here or here, it is already 0. So, you can call this to omega h. So, if you derive omega s equal to, following this omega h and sample this random process to get a sequence x n, then the corresponding discrete time autocorrelation function, or rather discrete time power spectral density phi e to the power j omega will be a replica of this. Go up to pi n minus pi, there will be no aliasing. So, if I now take that sequence and estimate its power spectral density, from that I can easily construct my analog power spectral density. Okay, this is an example. Now, so far we did the spectral analysis, we defined what is we gave the full all the properties of, we defined power spectral density both for analog processes and discrete time processes, we gave all the physical meanings, okay, and we carried out some examples. Okay. Now, from now onwards, for this lecture and next lecture, or maybe part of next lecture, I am not sure, it depends on how much time I have. Okay, I will be spending some time on methods of estimating the power spectral density. Again, power spectrum estimation is a full 1 semester course. So, obviously, in 1 or 2 lectures I cannot cover much, I will be covering some very basic things. Okay, there are actually two approaches, okay, two main approaches for estimating power spectral density. One is called parametric, another is called non-parametric. In a parametric method, whole estimation of power spectral density can be, it basically boils down to estimating just a few parameters of some model. Okay, that is also called model based estimation. That is actually a very powerful method that we will be considering after this. In a non-parametric method, what you have to do is that you are just giving a data record of that observed process, a discrete data record. Using that, you have to estimate the power spectrum, okay, without taking resort to any model, okay, or without mapping the entire problem to a estimation, to the problem of estimating a set of parameters. Okay. So, this non-parametric method the most popular case here is that of periodogram. Here you are giving a data record, there is some samples, however large be the record. Suppose you are giving the data record from 0 up to n minus 1. Something like this. Okay, and then you have nothing, you have 0, 0. Actually, it is not 0, but you do not have the data, you have data only over this period. So, using this data, what you first do is that you find out by some sample averaging technique, find out some estimate of the correlations. Okay. That is firstly how to find out the variance. You take each sample, take its mod value, square up the zeroth sample, square up the first sample, square up the second sample, dot 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 up to the n minus 1 sample, add all of them, divide by n. If n is large, this will be a good estimate. Okay, this is called sample estimate. So, if n is large, statistics can be used, and it can be shown that this estimate tends to a good estimate for the variance. Then how to find out the autocorrelation for lag 1? Okay, take the 0th sample, first sample. What is the lag? 1. So, x 0 into x 1, then take x 1 into x 2, then x 2 into x 3, then x 3 into x 4, dot 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 dot, go up to x n minus 1, x n minus 2 into x n minus 1, you cannot go beyond that. Add all of them, again divide by capital N. Okay. You get an estimate for autocorrelation with lag 1, then for lag 2, lag 4, lag 3, lag 4, so on, dot dot dot, so on so. Now, what happens is this, in most of the practical cases, the correlation is actually located mostly amongst the adjacent samples. That is, for low values of lag, okay, you have got higher values of correlation, and as lag or the gap between samples increases, naturally the mutual influencing capability decreases if the samples are far apart, and therefore, their correlation decreases. So, correlation has actually die out as the value of lag, that integer k, r of k, that integer k increases in either direction in magnitude. Okay. Therefore, if I have got a sufficiently large data record and I get estimate the autocorrelation for say lag 0, lag 1, lag 2, up to some finite number of lags, okay, it is enough. I can assume that since the autocorrelation is a dying function and I have already estimated sufficient number of autocorrelation figures for lag 0, lag 1, up to some lag, say capital lag, say up to capital L, okay, I can safely assume that subsequent values of the autocorrelation are approximately equal to 0 or can be neglected. So, I can rely on this, take them and use them to compute the discrete time Fourier transform, and that will be some idea of some estimate of the power spectral density. That is the philosophy of basic philosophy of periodogram. So, what I do here, you first estimate this for x n k. How you estimate? This way. Not k here. So, what I am doing, first take k equal to 0, that is the variance. That means, I am taking the summation from 0 to capital N minus 1, and what are the values? X say are equal to 0. So, x 0 into x star 0, that is mod x 0 square, then x 1 into x star 1, that is mod x 1 square, dot dot dot. So, each sample I am taking its absolute value, squaring up and adding, and then dividing by capital N. So, that will obviously give me the best estimate, the good estimate of the variance. Then consider lag 1. What I am doing? I am taking say x 1 for r equal to 0, x 1 into x star 0, then x 2 into x star 1, x 3 into x star 2, dot 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 up to what I am going? I am going up to n minus 2, okay, and k equal to 1. So, r plus k will finally become n minus 1. When r equal to n minus 1 minus k for a given k, this r plus k becomes n minus 1. So, this is n minus 1. So, in this case it is x n minus 1 and x star n minus 2. Okay. So, that means I am multiplying two samples at a lag 1 after taking conjugate of the second sample and adding and then averaging. So, that will again give me a good estimate of autocorrelation value at lag 1. Similarly, for lag 2. So, for a general case for the kth lag, what I am doing x k into x star 0 for r equal to 0, then x k plus 1 x star 1, x k plus 2 x star 2, dot 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 up to when r equal to this n minus 1 minus k, r plus k becomes n minus 1. So, x n minus 1 into x star n minus 1 minus k. So, again lag is k. So, they are added and divided, that gives an estimate of autocorrelation function with lag k. So, all remember, since I have got just a causal data record from 0 to n minus 1 and I found out r x x 0, r x x, I mean r cap is for estimate, r cap x x 0, r cap x x 1 dot dot dot. Then I use the fact that r cap x x minus 1 is minus k is. So, I get the other left hand side also, because I have to make it symmetric. Okay. And once I do that, then what is happening? Once I do that, then I take its discrete time Fourier transform. Okay. I take its discrete time Fourier transform, and that will be my periodogram. That is, just give me a minute. So, I have got now autocorrelation sequence from minus within bracket capital N minus 1 to plus within bracket capital N minus 1. Okay. And if I take its discrete time Fourier transform, I get that periodogram power spectral density, sorry, phi cap, because these are all estimates, periodogram e to the power j omega. What is that? This is say k equal to minus of n minus 1 to plus of n minus 1 obviously, and because of this relation you can easily see that what I get here, that will be a real function, that will be non-negative function, all those things can be seen. Okay. So, this is called the periodogram estimate. So, here actually computationally there is something, first from computational angle point of view, what you have to do, you have to first use the data to calculate the autocorrelation values, estimates, and then use the estimate in the DTFT computation. But there is one way where you can skip this intermediate step of calculation of the autocorrelation sequence, and you can directly obtain the same periodic this periodogram. Okay. We will go to that next. Okay. If you look at this expression, forget about the 1 by n factor, this part. If you look at this part, this you can write also as a convolution of what? These two sequences. Firstly, just a minute. I rewrite everything here because I need more space now. So, that this was according to us this. Now, you define, if you define one sequence x capital N N, that is a windowed sequence actually. And then 0 0 0. It is nothing but I am taking the 0th sample of x n, first sample, second sample up to n minus 1 sample. To the right of that n minus 1 sample and to the left of 0th sample, I am putting zeros. So, basically I am multiplying the original sequence by a rectangular window from 0 to n minus 1. Mathematically, x n minus n is equal to x n for n less than equal to n minus 1 greater than equal to 0 and 0 otherwise. My question is, if you convolve these two sequences, if you carry out suppose x this x n convolved with x n minus n, what do you get? You will see that we will get nothing but this term. So, for that you have to see how it is. What is x n? Sorry, there will be this is convolution and there will be a star. This star is actually, so let me put a circle here. The circle star is convolution and this star is conjugate. Okay. Now, what is x n minus n? I need some space, let me delete this part. This is your x n What is x n minus n? Forget about the star, we will assume that we are conjugating the samples, that is not important. X n minus n is the reverse version of that. So, just you will start at 0 and go up to minus of capital N minus 1. These two sequences, if you want to convolve, what you have to do? You have to again reverse one of the sequences. So, if you reverse the second sequence, you get back same one. Okay. I am skipping those step. X n minus n is what? That is a reverse version of that, which starts at 0 and goes up to minus of n minus 1. That is one sequence and another is x n n, these two are to be convolved. For convolving, what you have to do? Hold one sequence as it is. So, first sequence I hold as it is, second sequence I have to again reverse. So, I get back what it was earlier and then you have to shift it to the right or left by an amount at which by an integer say n or by an integer k, for which you want to find out the convolution. So, suppose I reverse it and now shift it say by k. So, that means at kth point I have got x 0 like this, and if you now convolve x 0 here, in fact I should say now x star, okay, x star 0, it multiplies x n k because this is the kth point. Okay. So, you get x n k x star 0, then x n n plus 1 sorry k plus 1 x star 1 dot 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 so and so, and then last one will be, because from this first sequence I can go only up to the n minus 1th point. So, x n n minus 1 into x star, the lag is k. So, n minus 1 minus k. This is precisely what we have within the sum, then 1 by n of course. Now, if this is so, as you can see, then of course, you can shift it not only to the right by positive k, you shift it to the left also by minus k, and you get both sided. Okay. So, you carry out the total convolution, we will get a correlation sequence, conjugate symmetric. Okay. If you now take, that will give you r cap x x k, okay. And you have to take the DTFT of that, as I said, discrete time Fourier transform, to obtain the discrete time power spectral density, which is the periodogram estimate of the power spectral density. There you can now see this summation is a convolution between x n n with x n star minus n. So, discrete time Fourier transform will be what? Convolution in time domain is product multiplication in frequency domain. So, that means phi cap period e to the power j omega, which is the DTFT of discrete time Fourier transform r cap x s k, that will be what? 1 by n, because 1 by n is as it is, and this summation in time domain is a convolution between the two sequences. So, in frequency domain, that will give rise to product of the corresponding discrete time Fourier transform. First one is, say, giving rise to what? After all, what is x n n? Maybe I can write x capital N e to the power j omega. What is that? That is the discrete time Fourier transform of that finite duration sequence x capital N n. That is the sequence which starts at 0, at x 0, x 1 goes up to x capital N minus 1, and then 0 to the right and 0 to the left of origin. For that sequence, the DTFT, discrete time Fourier transform, is x n e to the power j omega. Okay. So, that comes from the first term. If that be so, what is the Fourier transform of the next one? This is actually a basic, basic DSP fact, but in case you do not know, I have to do it again. X n star minus, what is the DTFT of that? It is a rough calculation I am making, I will erase it. Okay. Replace minus n, n by minus n, replace minus n by m. So, when n is minus infinity, m will be minus plus infinity, and when n is plus infinity, m will be minus infinity. So, it will be from plus infinity to minus infinity, but summation can be always, whether you take the summation from plus infinity and go to minus infinity, or from minus infinity to plus infinity, is one of the same thing. So, once again you get back m and minus n was m. So, it is the power j omega m. Forget, take the star out from here, put a minus here and star. This is nothing but conjugate of this x n e to the power j omega. So, that means you can say this is a real function, non-negative function and all that. This is the periodogram estimate of power spectral density. Okay. This is quite handy in practice. Only problem is, I mean, this actually often gives rise to biased estimate. Okay. The other version, the other approach is the parametric approach. model based. Here the entire problem of estimation of the power spectral density can be made to boil down to an equivalent problem of estimation of a few parameters of a model, and very sophisticated algorithms exist in literature. Okay. Now, before I go into that, just consider this scenario, that suppose there is a LTI system, linear shift invariant system of impulse response H n. It is excited by a white process U n, 0 mean white process, output is x n. Okay. So, since I do not have much time, in few minutes time I will just give a prelude to that, and in the next class I will consider it. Okay. So, U n is a white process, U n is a white process, that is 0 mean white process, this R u u k is some n into n is some positive integer delta k. So, if you take its DTFT, it is flat n. So, this is the power spectral density. What is phi x x e to the power j omega? By our relation, it is n, phi u u, this is equal to n, this is equal to n. So, you can write n times this. Okay. N is any constant, it does not change the shape of the power spectral density, it only says gain factor. So, essentially to obtain the power spectral density of the process x n, we have to just, if we know h e to the power j omega which generated this process, then we know the estimate, we know the power spectral density. Now, what we do here in parametric modeling, we go for some rational modeling of H n, rational approximation. Rational approximation means in general H z, which is the Z transform of H n, it may not be having a closed form expression firstly, and even if it is a closed form expression, it does not have to be a rational function. A rational function is normally a ratio of two polynomials in Z. One is numerator polynomial like b 1 Z inverse plus dot 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 b q Z inverse q, and here it is 1 plus a 1 Z inverse dot 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 a p Z inverse p. This is called rational model. Okay. We assume that H z is rational like this. This is a very special assumption we are making, and there is justification for it, which we will consider in detail in the next class. Okay. So, if you know that, that means the entire model is described by a few parameters b 0 up to b q and a 1 up to a p. Okay. If you know the parameters, you know what is H z, you know what is h to the power j omega, fine, and then you know what is the power spectral density. You can estimate capital N, even if you do not know, this is just a scale factor, it does not change the shape. Okay. This particular model, it has both zeros and pole, it is called the pole zero model, or sometimes it is called ARMA model, auto regressive moving average model. If only the numerator is present, no denominator, then it has only zeros, then it is called only moving average or MA model, and if it has, I mean, no zero, maybe a constant b naught only, and only poles, then it is called all pole model or auto regressive AR model. Of these three, AR model has been very successful in practice, it is one of the most celebrated thing in statistical signal processing, and we will spend our effort mostly for AR model estimation. Okay. Remember, in time domain this equation means what? If you call it H z equal to y z by x z is nothing but y n plus a 1 y n minus 1 dot 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 a p y n minus p is equal to b 0 x n plus b 1 x n minus 1 plus dot 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 plus b q x n minus q. So, we will consider from a given data record of x n, we will consider methods of estimating the model parameters by some sophisticated algorithms, and we will be considering mostly AR model, but before that I will give a justification for choosing such rational model. There is a solid theoretical justification which comes from something called Old's theorem, Old's decomposition theorem. So, this we will consider in the next class. Thank you very much. Okay. So, today we will be considering, as I told you in the last part of yesterday's lecture, I will be considering parametric method of spectrum estimation, that is spectrum estimation by modeling. And I already told you the elementary ideas of modeling, that is you assume that the process is generated by passing a white sequence through a rational LTI system of transfer functions say Z, which can be all pole, all 0 or pole 0 both, and therefore, the power spectral density of the received sequence would be nothing but mod square of h to the power j omega, h to the power j omega being the transfer function. So, mod h to the power j omega square into some constant, the constant denotes the input power spectral density. Now, input is white. So, input power spectral density is flat, which is equal to some constant. So, in this case the entire spectral density estimation boils down to identifying that model or estimating the parameters of those model, the coefficients that occur in the numerator and denominator polynomial in Z. Now, before I go further into that, I told you yesterday also that there is a justification for making this assumption and going by this method, and that comes from what is called Old's decomposition, a famous theorem by a great statistics person. His name is Old. It's called Old's this says that given any random sequence S n, you can always decompose it into two parts. Okay. One is x n, another is say z n, where x n is called non-deterministic part and this is called deterministic part. And these two are mutually uncorrelated. Okay.